This is the video for the calculations for the solubility product constant. There's 4 calculations that we have to be particularly concerned with, and the textbook homework will of course be done on a separate video. So we're just gonna work through the calculations on this part of the slide. Key word here being we learned how to write equilibrium expressions for saturated solutions. So whenever we write equilibrium expressions, that means that there's a saturated solution at equilibrium. That's what the equilibrium means. That means there's exactly the maximum number of ions that are present at equilibrium. And that's where the solution wants to be. It wants to be saturated. It wants to have exactly the highest number of ions present. Any more than that would be bad because that's oversaturating it, and any lesser than the amount of ions would be bad because that's undersaturated. You want to be saturated just like you want to be at equilibrium. Those mean the same thing essentially for a equilibrium with a dissolving salt in water. Okay, so a couple of things to note here. KSP is temperature specific and independent of the source of the ions. So it doesn't matter where the ions are coming from, whether they're coming from a salt or from an acid or a base in the case of hydroxide ions, but essentially, basically, the source of the ions does not really matter. All that matters is that the KSP is only affected by the temperature. Right, so we have our KSP values at the back of the textbook, and now we're going to determine individual ion concentrations using KSP values. So calculate equilibrium concentration of lead and bromine ions in a saturated solution of lead bromide. All right, so where are we? So we're doing lead bromide solid, lead ion plus 2 bromine ions. Solids don't count. 0, 0, x, 2x, x, 2x. Right, so this is going to be this is what our ice table looks like. And then this should obviously be 25 degrees Celsius. But from here we can go to our equilibrium expression, which basically states KSP equals x times 2x squared. Again, this is very important. The 2 from the coefficient shows up 1 when you're adding plus 2x, when you're doing that stoichiometric addition. And second, when you're raising it to the power in your KSP expression. That's also very important. So this is, again, 2x, the whole squared is x times 4x squared is 4x cubed. And this is equal to the KSP of lead bromide, which I will look at a back of the textbook chart and find that it is 6.6 times 10 to the power of negative 6. So what I want to calculate is the equilibrium concentration of ions, which is what are my x and 2x. So I will take my KSP, 6.6 times 10 to the power of negative 6, divide by 4, and then I will take the cube root of that, which will give me x equals 0.0118 molar, which means my lead ions are 0.0118 molar, and I multiply that by 2 to get 0.0236 molar concentration of bromine ions. So this is basically telling me that if I have this much concentration of lead and this much concentration of bromine, this is a saturated solution. So this is my maximum allowed concentration of these ions in solution. Any more than that, I'll be supersaturated or oversaturated. Any less than that, I'll be undersaturated, both of which are undesirable conditions for an equilibrium. I want to be at equilibrium, which means I want to attain these values in solution. And we'll see how that's going to happen. And this is basically going reverse. So the solubility is 2.2 times 10 to the power negative 4. This is basically giving you your x value, 2.2 times 10 to the power negative 4. This is the maximum number of ions that could be dissolved. So again, CaF2 solid, calcium 2 plus 2 fluoride minus, you know, the usual. You could do a 0, 0 plus x plus 2x, x, 2x. Again, x times 2x squared equals KSP, implies that 4x cubed equals KSP. But I know x is 2.2 times 10 to the power negative 4, so I just do 2.2 times 10 to the power negative 4, the whole cubed, multiply that by 4, and I have KSP is equal to 4.26 times 10 to the power negative 11. That's my KSP. So these were pretty simple. I either give you, you have to set up the exact same ICE table every time. I either give you the KSP, in which means you have to calculate x, or I give you x in the form of solubility or molar solubility, and you have to calculate KSP. So far it's so good. We are going to be talking next about the common ion effect. The common ion effect basically states, again, the x value that you calculate is the maximum. So when I dissociate, so I want to reach this x value, let's say for calcium, I want to reach an x value of 2.2 times 10 to the power negative 4. That's where I want to be at. And so this salt will dissolve until I reach that value. What happens when I already have some calcium ions present in solution and the starting one is not zero? That's basically what the common ion effect is. So if I already, so let's do it with one of these examples, calcium carbonate, right? So if soluble calcium chloride is added, that means I'm adding Ca2 plus and Cl minus, right? But I'm interested in this equilibrium because this is my equilibrium for the slightly soluble salt that I'm interested in. This is completely soluble, which means it completely dissociates. KSP is greater than 1. I don't care about how much this is dissociating because it's fully dissociating. But calcium 2 plus added will increase the concentration of calcium ions, which will shift the equation to the left, and that therefore decrease my solubility, right? Because I'm going to the left. Going to the left means I'm increasing my solid, which means I'm decreasing my solubility, because solubility is defined as how much ions or how many ions are produced in solution, right? So shifting a reaction to the left will cause precipitate to form, which means my solubility is decreasing. Again, it's just adding one of the products means that my reaction goes to the left. That's essentially the common ion effect, right? So we're going to compare lead iodide in pure water in 0.1 molar solution of sodium iodide. So again, sodium iodide is, if you look at the solubility chart, completely soluble. So there is no sodium iodide, there's just sodium ions and iodide ions, and 0.1 molar of each, right? So now, lead iodide in pure water, can find the solubility. So again, we can set this equation up so that it looks like lead iodide, lead 2 plus 2 I minus. I'm going to skip to the equilibrium step because it's 0. Oh, well, let's not do that. 0, 0 plus x plus 2x, x, 2x. And then I get x times 2x the whole squared equals KSP. So 4x cubed equals 7.9 times 10 to the power negative 9. And therefore, my x is 7.9 times 10 to the power negative 9 divided by 4. And cubed root of that answer, x is 1.25 times 10 to the power negative 3. So this is how soluble it is in pure water. So basically this x, so how much lead and iodide ions will I have? I will have 1.25 times 10 to the power negative 3 lead ions and 2.5 times 10 to the power negative 3 iodide ions, right? But what happens when I add sodium iodide? So here, the only difference is instead of 0.1, instead of 0, I have a starting concentration of iodide ions. So everything else is going to essentially x 0.1 plus 2x remain the same, except for this right here, where I do have x times 0.1 plus 2x squared. So what I'm going to do here is I'm going to use my small x approximation. I'm going to do initial concentration divided by KSP is greater than 500, so I can cancel out this 0.2x. So it's essentially 0.1 squared equals my KSP. So again, the KSP does not change because that's what the KSP does not depend on the source of the ions. It just depends on the temperature. So just because I have sodium iodide does not mean that my KSP will change for lead iodide, right? So here, if I calculate my x, I get 7.9 times 10 to the power of negative 9 divided by 0.1 squared. So x basically equals 7.9 times 10 to the power of negative 7. So in my solution, you can see that my x for lead ions has decreased greatly. And my solubility of lead iodide has gone down because I already had iodide minus ions. So again, the value of this concentration is basically 0.1 plus whatever little this times 10 to the power of negative 7 thing is, times 2, of course. But you don't really need to worry about that. The key thing is here, my solubility of lead iodide has gone down compared to here because of the addition of iodide ions from another source. All right, so I'm going to, most probably because of the calculations that are involved with the buffer solutions, which we said we would not do, there are not going to be, I think, questions, at least for this test, on the solubilities of these things. Common ion effect. You have to know that when I add a competing ion, my solubility decreases. That's the important point here. So, or when I add a common ion, sorry, not competing, common ion, my solubility decreases. So, there's that. This is more likely to come up. So again, this is basically where we're talking about molar solubility and KSP. So we have to understand that, again, when we say KSP equals like x squared or 4x cubed or whatever, 27x to the power of 4 or whatever answer that we get here, we have to be keenly aware that these are like related to each other. As molar solubility increases, KSP increases. As molar solubility increases, KSP increases, because there's no dividing by any x term, right? Because it's only in the numerator. So our molar solubility and the KSP are essentially related values that tell you the same thing. The higher molar solubility means more soluble. Means higher KSP also means more soluble, right? So here, what happens when you have a given concentration of salt? We want to find out whether it is going to form a precipitate, or the precipitate is going to form or not. And that depends essentially on the equilibrium that's set up. So we'll use an example of, let's say, barium sulfate for fun. This is going to dissociate into barium 2 plus sulfate minus ions. All right, and here again, when we get our solubility values, the solubility values are defined, again, as the ions that are present at equilibrium. So the system always wants to be at equilibrium. So when I calculate, at equilibrium, I get a KSP equals some x squared, and that value, this x value, is the solubility that the system wants to be at. So basically, if I have a QSP, so again, QSP is very similar to a QC calculation. It is not at equilibrium. So let's say I just add 0.1 moles of barium and 0.05 moles of initial. I want to find out whether this system, so if I do my calculation with the initial, it's a QC calculation. If I do my calculation with the molar solubilities or the equilibrium, it's a KSP calculation, QSP I should say here. But essentially what I want to find is, with these concentrations, is this more than, lesser than, or equal to the maximum concentrations that are allowed for my system? So again, if these concentrations are too small, that means my QSP is going to be too small, because QSP is essentially this times this, raised to some power if there's any coefficients, right? So that's my QSP, very linked to these values. So if these values are too small, that means my QSP is too small, and my reaction will shift to the right to increase my QSP, because again, I want to get to equilibrium, right? So my precipitate will not form if QSP is lesser than KSP, because my solubilities are not big enough. If QSP is equal to KSP, it is a saturated solution, which means there'll be no precipitate, but if I add more solid, I will form a precipitate because I am at a saturated solution. That's the maximum number of ions that can exist. If the QSP is greater than the KSP, which means that these concentrations are too big. So to reach equilibrium, I will shift in the reverse direction towards my solid, which will form a precipitate. Right? So again, let's do these ones again. If QSP is lesser than KSP, the QSP value is too small, which means my solubility, these concentrations of my ions here, are too small. That means that I will shift my equilibrium to the right to increase these concentrations so that I can reach my KSP value, reach my equilibrium state. If QSP is greater than KSP, these concentrations, ion concentrations, are too big. So I will want to decrease these concentrations by shifting my reaction to the left, which will cause the formation of my solid precipitate. So the precipitate will form if the QSP or these concentrations are too big. So let's do a question that kind of uses this. Will a precipitate form when 0.5 liters of that lead nitrate is mixed with 0.25 liters of calcium chloride? KSP for lead chloride. So when I give you the KSP for lead chloride, that's kind of the equilibrium you want to set up. But first we have to do a double displacement reaction. Lead nitrate, calcium chloride. All nitrates are soluble. And so therefore I think we multiply this. No, this is already balanced, isn't it? This is already balanced. So there's no ratios here, which is good. 0.5 liters of lead nitrate, so 0.5 liters, 0.003 molar. 0.25 liters is 0.001 molar. So again, with this expression, basically I'm interested in my solid that is forming here, because my next is going to be set up, my next equilibrium is basically going to be this solid plus water is going to dissociate in aqueous solutions to this and 2Cl minus, and I'm interested in my initial concentration, like what do I have here? Is that bigger, greater, or lesser than what I need in order to solve this question? Right, so what is that value that so this initial concentration, I can calculate with my initial concentrations from these salts, I can calculate my QSP and I look, okay, is my QSP, is it too small? Is it too big? So how is that going to affect my equilibrium? So I have to calculate these initial concentrations. So how do I do that? So how much lead ions are present in solution? So to calculate the lead concentration, we know that that's basically equal to my lead nitrate concentration, because it's one molecule of lead nitrate gives us 1 molecule of lead, and so my lead nitrate concentration is 0.003 times 0.5, but divided by 0.5 plus 0.25, right? And again, I've calculated number of moles and divided by total volume. So that's how I get this answer, because essentially I have to dilute it that many times. Okay, so let's move that. So the lead concentration will equal to my lead nitrate concentration, because there's 1 lead ion in every lead nitrate, and therefore the only calculation I essentially have to do is a dilution, because I'm adding 0.25 liters of something else, and even if that was pure water, I still have to do my dilution because I'm changing my concentration, because I'm adding some extra water or extra of some solution. Next we calculate our chlorine ion, which is basically 2 times the concentration of calcium chloride, because again, for each calcium chloride, there's going to be 2 chlorine ions that are being produced. So this is again equal to 0.25 times 0.001 divided by 0.5 plus 0.25, but times 2 because there's 2 chlorine ions. So I'm going to do that calculation. What did I do wrong? 2 times 0.25 times 0.001. 0.000666. That is my concentration of chlorine ions. And again, just because there's a 2 here, remember the 2 first comes up in my equilibrium step, so the plus 2x. I do not multiply this concentration by 2. So I can calculate my QSP by doing initial concentrations times each other, so 2 times 10 to the power negative 3. Times 0.0006 squared. So I do include that 2 in the coefficient here, so that's important. And my QSP is equal to 8.88 times 10 to the power of negative 10. Let's compare that to the KSP. The QSP is lesser than the KSP. What does that mean? If my QSP is too small, that means my concentrations, my initial concentrations here are too small. That means my precipitate will not form, right? Because all my ions will stay as ions. Even if I add more solid, they will still dissociate into ions because I still haven't reached my equilibrium state yet. And so therefore, that's how you figure out whether a precipitate is forming or not. So next we will do some textbook questions to get better at doing these calculations.